Okay, hi everyone. So in this video, we're going to be finishing up our study of vector spaces. So let me just quickly recap where we're at and what we're going to be doing here. So one of the last things we showed, so this is the course notes, was this corollary. And it says that if V is a n-dimensional vector space, and R is any positive number where R is smaller than the dimension, if you take a set of linearly independent vectors of V, so if the dimension is 10, let's say you have 5, so you could take 5 linearly independent vectors of V, then you could find vectors. So if you have, if the dimension is 10, and let's say you take 5 linearly independent vectors of V, then they're saying you could find a sixth, seventh, eighth, ninth, 10th vector such that all 10 of these is a basis of V. In other words, this result is telling us that every finite dimensional vector space has a basis. Why is that true? I have a remark over here. Okay, so this corollary was saying that for a finite dimensional vector space V, one can always start with any non-zero vector V. So all you have to do is put any non-zero vector V in a set by himself. This set is linearly independent. So once you have a set containing one vector that is not zero, that set is always linearly independent. And you then invoke this corollary. This corollary then says that you could take this linearly independent set and extend it to a bigger linearly independent set that will be a basis for that vector space. So that corollary says every finite dimensional vector space has a basis, and it tells you how to construct it. So what we're going to do in this video is we are going to show a more general result than this, in that we're going to remove the assumption of finite dimensional. And we're going to show that any vector space, whether finite or infinite dimensional, has a basis. Okay, and for that one, we need to invoke we need to invoke Zorn's lemma. So for that, so I know we already did this in class, but let me recap it. We need a couple definitions. So one of them was what is a partially ordered set. So a partially ordered set or PO set is a pair, so a set P with some sort of relation that we represent by less than or equal. And this relation satisfies these three conditions. So partially ordered set is a set with a relation that satisfies reflexive, transitive, and not symmetric, but anti-symmetric. Again, anti-symmetric just says if you have two elements in P, if x is less than or equal to y and y is less than or equal to x, then they must be equal. So the best example of these things is just to take as P, for example, the real numbers, and take as this as the usual less than or equal for real numbers. So if I tell you I have two real numbers, A and B, right? Um, so if I tell you I have two real numbers, A and B, and that A is less than or equal to B and B is less than or equal to A, then of course you will tell me that these two numbers must be equal. Okay, so this is an example of that. Um, Another example of this is set inclusion. So let me go to the side here. Yeah. Yeah. So another example of that is if you take as P the power set of some set X, right? So you have some set X, you take the power set of X, So this is the collection of all possible subsets of X, and you take as the relation inclusion. So set inclusion of subset. Then clearly, so these are just sets. Then of course you know that given any set A, B, C belonging to the power set of X, then of course you know every set is a subset of itself. So reflexive is satisfied. Of course you know if A is a subset of B and B is a subset of A, then A, it must be equal to B, right? So this is anti-symmetric. And of course, you know that if A is a subset of B and B is a subset of C, then of course A must be a subset of C. So this is transitive. So another example is you take any non-empty set, the X, or you could take an empty set, it so works. So any set X, you construct its power set. This is the collection you're looking at, and the relation will be usual subset. This forms a partial ordering on P of X. And in fact, when we go to do the proof that any vector space has a basis, this is exactly, well, we're not going to use the power set of X, but this is the relation we're going to use, inclusion. Okay, so that's just another example. So it's good to know a next example other than the regular numbers. So let me just go back to this. So something to note about this is that if I take any two elements of the power set, for example, if I say let A and B be any two elements of the power set of X. So what does that mean? That means A must be a subset of X and B is a subset of X, right? So again, the power set is the set or collection of all possible subsets of X, right? And if X is finite, the number of elements is 2 to the cardinality of X. Okay, so if I take any two subsets of X, my question is, can we always say that either A is a subset of B or B is a subset of A? Could we always compare two elements under this relation? And the answer is, of course, no, right? Because, for example, let's say X is 1, 2, 3, 4, 5, right? Let's just say, and give me two subsets of this. Let's just say A is 1 and 2, and let's just say B is 2 and 3. Okay, so B is 2 and 3. Okay, so clearly A and B are subsets of X, but A is not a subset of B, and B is not a subset of A. In other words, even though I know this is a partially ordered set, right? Because I just argued that in this section here, this is a partially ordered set, right? If I take any two elements from that set, in this case, the set is power set, there's no guarantee that I could compare these two elements together, right? So I need to be able to compare every single element to each other. Of course, in the real numbers, that is of course, you could do that because if I give you any two real numbers, right? Any two numbers, you could of course tell me which one is less than the other, okay? But if I give you any two sets, it's not always true that one is going to be contained inside the other, right? So we need a different type of ordering for this. So when we have a partial ordering, like we did over here, and the extra condition, that any two elements we take from it, we could always compare it using the relation, the partial ordering. We call that a total ordering or a linear order. Okay, so totally ordered set is a partially ordered set from before. It's called a total ordering or a linearly ordered set if for any two elements we could compare them. Either x is less than or equal to y, or y is less than or equal to x. That is, we usually say any two elements are comparable. So you can always compare them together. Okay. Yeah, so two more things we need. One is what is an upper bound? So once we have a partial ordering of some set, if we take a subset of it, A, we say an element U. So notice that this element U just has to belong to the big set, not necessarily to A. Okay, so U belongs to P. It's called an upper bound for A if every element in A is less than or equal to every to this element U. Okay, so everything in A is less than or equal to U. So this is called an upper bound. This is the same upper bound that you would have met in your real analysis course. And now we need something something very similar to it. There's a subtle difference, and that is the idea of a maximal element. So again, we have a partial ordering. We say that the element M, and again, this element just has to belong to the big set, P, is a maximal element if there is no other element in P such that M is strictly less than X. So notice that in the ordering here, we just defined less than equal. We didn't define what this symbol means, strictly less than, but I put it over here for you, right? So another way of saying this is here. So an element is said to be a maximal element if M is less than or equal to an element X always implies that X must be equal to M. Okay. So for example, what if I take a P 1, 2, 3, 4, right? And I take the usual less than or equal. Then I could say that 4 is the maximal element, right? I could say 4 is the maximal element since if any element X is, sorry, 4 is less than or equal. Since if 4 is less than or equal to X, right? Then X must be equal to 4, right? If I tell you I have an element X belonging to P, such that 4 is less than or equal to X, then you will conclude X must be 4. So that is a maximal element. Okay, and finally, what does Zorn's lemma have to say about this? So Zorn's lemma is saying that if you have a partially ordered set, right? So P with the ordering less than or equal, if every totally ordered subset, yes, so something I forgot to put in over here is that a totally ordered set or a linearly ordered set is also called a chain. So there's a lot of different terminology for this, right? So it's sometimes called a chain. So Zorn's lemma is saying we have a partially ordered set. If every totally ordered subset of P has an upper bound in P, then P contains at least one maximal element. Okay, so it's saying so P just has to be a partially ordered set, right? So we know that any two elements in here that I take, if I take any two elements of P, I may not be able to compare them because P may just be a partially ordered set. So I can't guarantee that I could compare any two elements that I randomly pick from P. However, what this is saying is that if you take, for example, a subset of P, and A is a totally ordered subset. So if every single totally ordered subset you take from it, so totally ordered means you could compare any two elements to each other. You could say which one is the bigger one. If every totally ordered subset has an upper bound in P, then the set P has at least a maximal element. Okay. And Zones is very useful in proving the existence of objects without actually showing how to construct it. So in this proof, we're going to show that. So here it is. Every non-trivial vector space V has a basis, but we're actually not going to show how to construct it, right? The use of Zone's lemma is once you have a clever choice of what this guy P is and what the ordering is, then all you really have to do is show that this part is true. Every totally ordered subset has an upper bound in P. And then Zorn's lemma, you invoke it and you get for free a maximal element inside of P. And because of your clever choice of what this guy P is, you'll see it in a bit what I mean by clever choice of P. Because of your clever choice of what this set is, this maximal element will be what you want. It will be the object you are looking for. Okay. I think this maximal element is unique. I'm not too sure, but I'll have to check on that. Okay, so the proof, it looks a bit complicated and intimidated at first until you realize that the only thing you need to remember is that you need to invoke Zorn's lemma. So you just need to figure out what are you choosing for P and what is your partial ordering. And then all you have to do is show that every totally ordered subset has a upper bound, and then you get the maximal element for free, and the maximal element will be a basis. Okay, so let's see how to do this proof. So every non-trivial vector space V has a basis. So first, we're going to let L be a set of linearly independent vectors in V. So just like before in this corollary, or rather in the remark on how to construct this basis, I said, okay, you just take a set with any non-zero vector that is clearly linearly independent, and then you just invoke this corollary to extend this guy to a basis of the space. We're going to start in a similar way. Okay, so we're going to um, uh, first take a set L to be some set of linearly independent vectors in V. So for example, you could simply take L equals V1, where V1 is some non-trivial or non-zero vector in V. So that is linearly dependent. Now you're going to let J, so this is a fancy J, be the set of all linearly independent subsets of V that contain L. So right, so here's V, here's L, right? This is L, and L is linearly independent. What this thing J is you're going to take all linearly independent subsets of V, that's these red circles, that contain L, right? So the collection of all of these red is this fancy J. Okay, so J is the set with the collection of all linearly independent subsets of V. So they are all linearly independent subsets. But the extra condition is that L is inside of all of them. And we're now going to put an ordering on this collection J. Okay, so this collection J is like P in the partial ordering before, and the less than or equal is set inclusion. So it's going to be partially ordered by, so you see inclusion here, inclusion is subset. This. This is inclusion. Okay. So what I'm working with is this J, this inclusion. Okay, so this turns out to be a partially ordered set. Okay, so then this guy is non-empty. Why is it non-empty? It's non-empty because L itself is an element of J. Because remember, L is linearly independent, right? L is linearly independent. L is clearly contained in V, and L is a subset of L, right? So L is contained in L. So L satisfies all these conditions. It is it, it is a linearly independent subset of V that contains itself, L. So L is inside of here. So therefore this collection is non-empty. Moreover, if so now so this is the partial ordering. Now what we need to argue is that every total ordering of this, so every chain, so we're going to take a subset of it, um, has a upper bound. And to construct the upper bound, we'll see is actually not very difficult. So if J1 is inside of J2 and J2 is inside of J3 and so on, is a totally ordered chain of subsets in J, right? So right, so we just need to refer to what is going on in Zorn's lemma. So Zorn's lemma require this. That's what we have. So we're just filling in everything we need in Zorn's lemma. If every totally ordered subset chain of P, so we need to construct a chain in here. Okay, so chain again means every two elements are comparable. So now J, remember the elements of J are subsets, right? These are the elements of J. They are subsets, right? They are linearly independent subsets. So what we're doing here is we're taking a bunch of them, right? So J1, J2, J3, J4, and so on. But remember, um, we're going to assume that it's a totally ordered subset. So totally ordered means we could compare them, right? We could list them in this way. So, so I took this from a textbook, and usually in math textbooks, when they use subset, they actually mean subset or equal, right? So this is just because you see, for example, J1 subset J2, that does not mean it's J1 subset but not equal to J2, right? Textbooks usually just put this symbol alone. They don't usually put the line below. Um, okay, I need to remember to change that. So we're going to take a total ordering, right? So this is a total ordering. So we collect a bunch of these guys, and that allows us to order them. The J1 subset of J2, and J2 is inside of J3, and J3 is inside of J4, and so on, right? So we need to now argue that, so now this is an arbitrary uh, total ordered subset of this big guy. So I now need to argue that this thing, this total ordering, has an upper bound. So there's an element up here such that all these guys are less than this element. So by less than, I mean subset. So the most obvious thing is if I have, remember the J's, we're treating them as elements, but they are themselves sets, right? So if I want to construct something up here, that J1 is inside this guy, J2 is inside this guy, J3 is inside this guy, right? All of them is inside this set, this element. Then it makes sense to just take the union of all of these J's, and that might be the upper bound. And that is exactly what we're going to do. We're going to define M to be the union of all of these J's. Okay, so we're going to union all of these J's. Now I need to argue that this M is an upper bound for this chain. Okay, so not only do I need to argue that this M is an upper bound for this chain, which is the obvious one, remember that this, according to Zorn's lemma, the upper bound must be inside of the must be inside of the set. So this M must be inside of this fancy G. In other words, this M that I have just constructed must be linearly independent subset of V, and it must contain L as well. Okay, so now we just need to argue all of that. So first of all, why is this set linearly independent? So each of these J's are themselves linearly independent. If I union all of them together, it's not necessarily true that their union will be linearly independent. But what we need to remember is that each one is inside of the next one, right? So M is also linearly independent subset of V containing L, right? It's containing L. Well, the reason why it's containing L is because remember, every single one of them contains L, right? L is inside all of these. So of course, M contains L. So why? So this one, right? This one is easy. All of the J's contain L, so clearly M contains L. But why is M linearly independent? Well, if I take now some vectors v1, v2, v3, vn belonging to M, and I form this linear combination and I put it equal to 0. Remember, that is how we show linear independence. If these vectors are indeed linearly independent, the coefficient, these r's, must all be 0. Okay? So all of these v's belong to M, right? All of these v's belong to M. But what is M? M is a union of all of the j's. So V1 must be inside of one of these j's. V2 must be inside of one of these j's. Vn must be inside of one of these j's, right? So there's a j in here that is going to contain at least one of them. In fact, there's a j in here that's going to contain all of them because they are all nested. Okay, they are all one inside of the other. So that's what this part is saying, where Vi is contained inside of J alpha I, right? Alpha I, because I don't know if V1 comes from J1. I don't know if V2 comes from J2. V5 might come from J50, right? So the index here, where you see the index depend is alpha I, so don't get scared. All that is saying is that the index depends on the vector V. So depending on which V you're looking at, it might come from a different J. So V1 may not necessarily be from J1. It might be from J3. Okay. So what we're going to do is the alphas, so the alpha i's, these are just natural numbers, right? We're going to let alpha now be the maximum of all of these numbers. In other words, so let me give you an example of this, right? So let's just say, right? So I'll give you an example so you actually see what's going on. So let's just say we have R1, V1, plus R2 V2 plus R3 V3 plus Rn Vn, right? And we have a chain. J1 is inside of J2, is inside of J3, is inside of J50, inside of J51, something like that, right? Let's say V1 came from J5. Let's say V2 came from J2. Let's say V3 came from I don't know, 55. Let's say Vn came from J1. Right? And let me say all the guys in here came from between J7 and J29. Right? Just making up numbers. So what we're going to do is we're going to compare all the index. So 5, 2, 55, 1, 7 to 29. Take the largest one, 55. Right? So the alpha you see there. So this is alpha 1. This is alpha 2. This is alpha 3, and so on. So alpha is the maximum of all of the alpha i's. In this example, alpha will be 55. Okay, so J55. So why is this alpha, the maximum of them, so important? Well, J1 was in J2. J2 was in J3. So look at this. Vn was in J1, right? So therefore, Vn is in all of them because J1 is in J2, J2 is in J3, J3 is in J4, and so on. So everything in J1 is in everything after. Everything in J2, for example, V2 is in J2. So V2 is in J3, V2 is in J4, V2 is in J50, V2 is in J51, right? So everything in J3 is contained in all the J's after it. So if I have J55, okay, then all of these V's are in J55 because at least one of them was in a J before. Okay, so all of them are in J55. And what do I know about J55? All the J's are linearly independent. So this is a linear combination in J55. And J55 is linearly independent. Therefore, all the R's must be 0. Right? So, so let alpha be the maximum. So there are at most n distinct alphas. Yeah, so this should be an alpha, not an A. And each is a natural number, so we could find alpha. But then all of the vectors are in J alpha. So in my example, alpha was 55. Okay, and since J 55, right, is a linearly independent set, then all of the R's must be 0. So that is how we argue that that this set that we have constructed is linearly independent. Hence, no dependence relation can exist among the vectors in M. So M is linearly independent set containing L. And if you are a linearly independent set containing L, right, then you must be in J. Right? So M must be in J. So we have this part. We have constructed an element in P. Now we just need to show that element is our upper bound, and it will give us for free a maximal element. So the upper bound part is clear because upper bound means all of these j's is less than or equal to m. Now, in this case, again, the less than or equal was set inclusion. So clearly J1 is a subset of M. J2 is a subset of M. J3 is a subset of M. Right? So it is also clear that by construction that M is a maximal element for the chain. Right? Maximal element, or is it as an upper bound? I'll have to check this. I think there should be an upper bound. That M is a maximal element for the chain. So I think there should be upper bound for the chain. Since every element in J has a maximal element, J itself has a maximal element. Call it B, right? So it's saying that this guy here has a maximal element. Now over here, you could then just invoke the fact that if you have that a basis is a maximal linearly independent subset, but if you want, we could say, set W to be the span of B. If W and V are the same, then B is a linearly independent set spanning V, so it's a basis. So suppose that V is not equal to the span of B, which is W. Then there exists a vector V in V, but not in W, right? But then we have no dependent relation of this form, right? So if this vector V is in V but not in W, then I could write this relation using vectors from V so that this set is linearly independent set containing L, but it's a linearly independent set, but it contains another element. But B was maximal, right? So maximal means that this guy should have been in B. Okay, so that contradicts the maximality of B. So therefore, no such V can exist. So V is equal to the span of B. Yeah. So let me just go through something. Okay, so this part here, so what it's saying is that V belongs to this guy, but V is not in W. And remember, W is taken to be the span of B. Okay, and B was this maximal element. So what this is saying is, so why did they say we could have no dependence relation of this form? So if it was, if, so let's say A is not equal to 0, right? Then that means you could solve for V. So if A is not 0, solve for V. So V is minus A1 V1 minus AN Vn. Then we have 1 over 8, right? But this means that V, this is a linear combinations of vectors V1 to Vn. So that means that V is in the span of B, which is W. But I assume, oh sorry, V is not. But I assume V is not in W. Okay, so that's a contradiction. So therefore A must be 0. Right? And if A is 0, then this goes away. And all these A's are zeros because they belong to B, and B is linearly independent. Um, what I have to change is, where is it? Yeah, so there's some typos here I have to fix. So this guy here should be alpha I, and the biggest typo, this part here is a upper bound, right? Upper bound. Okay, so I will change those stuff. Okay, yeah, so that is the every chain has a upper bound, right? Upper bound, not maximal element. Maximal element is what we want to get, right? So make those changes in your notes if you have it, and I will make it in the course notes as well. Okay, thanks.